This is Jack Creel, and I'm going to be running through my calculation answers for homework 3. So the first problem is about heat transfer through a window. And so we draw our picture diagram here and our resistance diagram. The only assumption we really have here is that we're disregarding radiation. And then we know the overall heat transfer can be calculated using all the resistances and the overall temperature gradient. And so we calculate our area of the window, and then we go through and calculate each of these individual resistances. We have our two convective ones here and our conductive resistance here. We go in and plug all those values into this equation right here, and we find that our overall heat transfer is about 707 watts. And then it wants us to find the temperature at the inner point of the window as well. So I have that marked as T1. And we can do that by, instead of doing the overall heat transfer, we just focus on this part here. So just the temperature gradient from the ambient inside to the inner surface of the window over the one resistance there, the convective resistance. And we find that the inner temperature of the window should be about 4.36 degrees Celsius. The next one is about heat transfer through a little bit more of a complex system. We have sheetrock and then fiberglass and wood here. And so we draw our picture diagram and our resistance diagram. And so this wood fiberglass system is repeating vertically every 65 centimeters. So I'm going to use 65 centimeters vertical or height and 1 meter depth just to simplify things for my representative section here. And so just as we have in the past, we're going to go through and solve for all of our resistances. The only difference is that this time we have a couple of resistances in parallel, the wood and the fiberglass. So to find the overall resistance of those, we use this equation for resistances in parallel to get the overall resistance. And then the rest of it is pretty much the same. We're going to add all of the resistances up to get our total resistance here, and then use that to get the total heat transfer, which is about 406 watts. The next problem is about heat transfer through a cylinder here of water flowing through here. And so we do the same thing, picture diagram, resistance diagram. We're assuming that the pipe's a gray body, the surroundings are a black body, and the surrounding temperature outside is equal to T infinity 2. And that's given in the problem statement, so it's not really an assumption. Start with our inner and outer area, not different by much, just this thickness here. And then again, solve for all our resistances. This time we're going to use that cylinder resistance. And then also, this time it's different because we do have to take into account the radiation heat transfer coefficient. So that's solved with this equation here, which we mostly have, except for the temperature that we need here. And so we're going to have to guess at that, and I'm going to go with a guess of 80 degrees Celsius. And then we add up all of our resistances to get the total resistance and use that to find our overall heat transfer. And this isn't going to be totally right because we guessed at the temperature. So now we have to go into Excel and iterate to find the actual temperature. So I wasn't far off. The actual temperature is going to be 77 degrees Celsius here. And that will give us an actual heat transfer of about 2,220 watts. And then we can find the average velocity here. We find the mass flow rate from this equation, and then we can convert that into a linear velocity with this equation. And finally, the last problem is about mass diffusion of hydrogen through a membrane. And so we have this equation here, pretty similar to heat transfer for conduction. And we have pretty much all of the values from the problem statements. We just need to go through and plug and chug. And then this will give us the molar rate of diffusion, and we can convert that to a mass rate of diffusion just using the molar mass.